Hello everyone, really nice to have you here, and thank you for the organizer for inviting us actually. And we'll start today with a talk for you. From zero to production hero log analysis with Elasticsearch, and not only, because we'll start from, we'll get you through the whole pipeline actually. So before we start, I'll repeat the introduction a bit. I'm Rafal. I've wrote a few books about Elasticsearch, Solar. I work in a company called Sematext, where we do this kind of stuff like log analysis, etc. I'm father, husband, actually father of those two kids at the, down there, and
yeah, I'm Radu, and I just basically copy him. I also work at Sematext. I also wrote a book. You know, production support check, consulting check, log analysis check. Wife and kids check.
Okay, about our company a bit. It's located in New York City, right here, the headquarters. But we are distributed among the whole world, basically. We have people in Croatia. I'm from Poland. He's from Romania. We have Canadian guy. We have Vietnamese guy. So more or less the whole globe. We provide certain big data consulting and production support with SLAs and stuff like that. So if you are interested in that, maybe. We also do trainings for Solar and Elasticsearch. One is coming in soon, by next week actually. And we also have a lot of products like SPM and Logzine, which you can get log analysis and performance-related metrics for various systems like Elasticsearch, Solar, Kafka, JVM-based apps, HBase, Nginx, Nginx Plus, Apache, MySQL, etc., etc. But let's get on with today's talk. The agenda is like this. So we'll start with showing you the actual output of what we will achieve by doing a few steps. So we'll show you what we can do with the logs actually, where we already have them stored in Elasticsearch indexed in a proper way. So we'll show you Kibana. Then we'll take a step back actually to the beginning, and we'll tell about Elasticsearch essentials, how it tunes, how it scales, and what you should do, and how basically the best practices around Elasticsearch and log indexing. We'll show you Logstash, the tool that will be able to process the raw logs from your machines and send them to Elasticsearch. We'll introduce you to our rsyslog. Similar to Logstash, it will also get the raw logs and send it somewhere. And finally, we'll show you the whole pipeline where Logstash rsyslog works together with Elasticsearch and some kind of middleware buffer like Kafka. The most important thing about this slide is the address down there, github.com, Sematext velocity. All the commands that we will use during the tutorial today are available there. So you don't need to write anything. They are available there just to copy paste for you. And also there is prerequisites for all the stuff. So if you have a pure clean virtual machine that was just installed, you can get the commands to copy paste them, run through it, and you'll get similar behavior. And
yeah, that'll be me next.
Yeah, so I'll give the voice to Radu.
Right, so we'll start from the end, okay? Let's just assume that everything went well. We got our logs into Elasticsearch. And so the whole point being that you would be able to then search and analyze them. And you would normally do that through a UI. It can be Kibana, which is the most popular one. You can build your own on top of the Elasticsearch API. Anyway, so you have this query language. For example, you can search in a field, let's say in the agent field, and I would look for a string called Mozilla, okay? And yeah, you would see there the logs highlighted and so on. And you can build more complex stuff. So you can say and I don't know, something else. You can also use, for example, wildcards. That'll be a bit more expensive, but it should work, okay? You can also do things like fuzzy searches. So let's just say I forget one of these L's, and you know, I want to tolerate typos, so I just put that thing there, and I allowed for one change. And then again, after a bit more thinking, it will find what it wants. So this is basically like a high-performance grep, if you will, across your logs. But the really nice thing is if you can parse like your raw logs into everything in its own field, like in this case I have Apache logs indexed So if you have like a response in its own field, user agent in its own field, and so on, then you can do really powerful stuff in terms of analysis. So with Kibana, you can like build these charts, which you can then combine into dashboards. So let's just create a chart for the fun of it. New search, I guess. No, new search wasn't the thing, but anyway. Right, so this is it. No results found. Okay, because these logs are very old. Relative. I want them from 15 years ago until now. All right. So you found something. It's just one bar, okay? So I'm going to say on the x-axis, I want to build a date histogram, which is pretty much what you've seen before, the amount of logs per time interval. So if I do that and then just hit play, it should give me what I want. Oh, okay. I need to sort of zoom in.
Nine years worth of logs.
Yeah. And everything is squeezed in a few minutes, so I really need to zoom in. There you go. All right. But the really cool thing is that you can sort of drill down even deeper. So for example, okay, I have here more logs in certain time frames than others, but is it like legitimate traffic? Or do users hit errors? So you can do something like drill down, like add sub-buckets and say, for example, split bars by response code. So I'm just going to do a terms aggregation. We'll talk about what aggregations are in just a bit. And I'm going to run that on the response field. This assumes that I have my response codes in a specific response field and not like dumped into a huge string. So now if I do this, it should give me, for each time frame, it will give me the breakdown. Like these are all 200s. And yeah, I have other error codes here, response codes. Yeah, so this is, you can do lots of stuff, obviously. We cannot go through everything you can do with Kibana, but that's the basic thing. If you can think about something, you will just sort of build those pretty dashboards. And yeah, we'll go on to Elasticsearch and the juicy bits. So,
thanks. Yeah. And the perfect thing about Kibana is that it's just point and click, right? So you just click through it. So you have to see anything. The question is, why Elasticsearch works so well when it comes to searching through all that billions of logs that you have in your indices? The thing is that it works on the top of Lucene, Apache Lucene library, actually. It is the most known and actually most used open source full text search engine library written in Java. And it does some magic to the documents. We talk to Elasticsearch using JSON, so you can see a simple, very simple document with a single field called verb, and the value of that field is get. It can be a part of an access log or anything like that. This is a document. What we can do in Elasticsearch, we can actually store and index those documents. So when we store it, we are able to retrieve the original value, like for display purposes. We can just get it and display it. This is called stored. Radu will tell about how to configure that in Elasticsearch itself. I'm only covering the theory. So, and when indexed, Elasticsearch builds, using Lucene library, builds so-called inverted index. So instead of document and column-based data structure, you have a term-based data structure, which is inverted to what we know from relational databases, for example. So instead of having a document column and the value, we have a term, like the get, and the identifier of the documents that have that term in them. So this is a simplified view, of course. But, so if you would like to find all the documents that have the get term in the verb field, we would know that only by traversing through a single structure called term dictionary and getting those numbers. So we know that the get term, if we would have a few documents, that the get term would be in a document with ID 1, 3, and 5. And the put in documents with ID 2 and 4. And to get you an idea on how that actually works inside of Elasticsearch, we, not here. So these are the requisitives I told about. So I'll show you how that all works in Elasticsearch. First of all, I'll delete all the data so you know that I'm not cheating. Let me use not that one. So we talk to Elasticsearch by using REST API, HTTP protocol, and the standard HTTP methods. Like you do get when you want to retrieve data from Elasticsearch, you do put or post when you want to update or insert something into Elasticsearch, and you delete when you want to delete anything. So when we run the delete localhost all, that means that we just deleted all the data in Elasticsearch. Pretty destructive if you run it in production, but that can be controlled. That happens. Really, it happens. So now let's index a single document. You know, as I told, we provide SLAs for clients, and yes, that really happens. And now let's try to index a single document. The thing to remember about Elasticsearch is that a single document is always identified by three things. The first thing is the index that it needs to be put in. We need to specify it. In that case, the index name is the logs here. Then each document in a given index have a type and the identifier. We could omit the identifier and Elasticsearch would generate one for us, but in that case we won't do that. We will just specify it. So we tell that that this document will have an Apache type, which can, for example, show this is an Apache access log or anything. That helps us having multiple types of data in a single index. It's sometimes nice because logs can come from different sources, they have different structure, and we want to differentiate them somehow. Then is when we can use types. And we have the identifier, which is one. As a payload to the request, we provide the document, which has three fields: the verb, which is equal to get, the path, and some kind of bytes, probably number of bytes or the size of the document. If we will run that index, we'll see that Elasticsearch responded with some JSON as well. The document has been indexed into index called logs, type Apache with that identifier. It has a version of 1, which means that it was not modified previously. It has the first version. Some information about the shards, and the document has been created, which is set to true. So that's fine, we have the document. Let's now try running a single query. Again, as I said initially, we always talk to Elasticsearch using the HTTP API. Of course, there is a Java API as well that is used internally by Elasticsearch, but we'll today talk using the HTTP API only and using curl. So now we run a simple query against Elasticsearch. Elasticsearch has a really extensive query language called query DSL that is actually corresponds to Lucene and all the objects in Lucene internals. But this is what to know about this query. It is a Boolean query that allows us to specify the ands, ors, must not, etc. But it also allows us to do filtering. And for filtering, we'll use a simple query string that allows us to provide a query. In this case, the query is get me all the documents that have the get term in any of the fields. Why in any of the fields? Because internally, Elasticsearch uses so-called all field that it uses to copy all the data from a document to a single field to allow for easy searching on all the data without knowing the details like the field name and stuff. Now if we would write get the query, you would see that we have the documents. We have the documents, actually a single document around here that is in that index logs with the type Apache with the ID of 1. And one of the important things is the source that was returned, another special Elasticsearch field that provides us with a view of the original document we've sent to Elasticsearch. This is usually useful for two things. First of all, display purposes, and second of all, for example, for scripts where we update the document or anything like that. Usually in logs use cases, that's not happening. But we can also run a more sophisticated query. It is actually not that sophisticated, but we can specify the field using the path and the value. One thing to notice here is that we actually wanted to get documents with path index.html. Actually, the path is the name of the field. The index.html is the value, and we got the document which is /index.html. We'll tell about analysis in just a few minutes. So this is one thing. However, if you remember the Kibana that Radu showed, there was those nice graphs there. So how to calculate? Do you have to actually go through it, code that stuff, and calculate the values yourself? The answer is, of course, no. Elasticsearch has a framework called aggregations that allows us to calculate values from the data returned by queries. For example, in that case, remember the first thing that Radu showed is that we had the number of logs, right, for a given term, and this is what this aggregation is the terms. Let me show it once again. The terms aggregation is all about. You can see that the aggregations are structured like this. We add to the standard query, we add the aggs section or aggregations, whatever we like. Aggs is just simpler, and we give the aggregation the name, and we provide the type of our aggregation. This time, we want to get the terms aggregation, which means that Elasticsearch will return so-called buckets with the term and the number of documents the term appears in. What are buckets? Elasticsearch, again, provides us with two types of results returned by the aggregation. First of all, we have metrics, which is a single value that is returned. Second of all, it's the buckets, which are 0 or more. Let me show you what buckets actually are. So a bucket is a key and a count associated with it. And in that case, we have because we only have a single document, so that example is pretty simple. For that terms aggregation we just used, we have a single document that has the get term in that verb field, and the doc count, which means the number of documents that term appears in, is 1. I'll tell you what the terms are and all of that in just a second. And what's more and what's powerful about aggregations is that we can actually nest them one inside each other. If we only have enough memory and enough physical nodes of Elasticsearch to handle our queries, we can do that. We can do whatever we want with aggregations. So in that case, we would like not only to get the top term for the query, but also know the average inside a single bucket. That's why we included another aggregation here. Let me highlight that here, which we called average bytes per verb. And we've used an aggregation called average that should work on the field bytes. And what Elasticsearch will do actually, it will take the bucket, the documents inside the bucket, and will calculate the average value for that field we've specified inside that bucket. And we'll do that for every bucket that will be returned. If we would now go here and paste the query, we can see that for our buckets, in addition to the counts we've got initially, we have that average bytes per verb calculated. Okay. I think. Mm-hmm. So now, again, Radu.
Right. So we spoke about terms quite a lot, and these are. I'm good.
You good? Okay.
These are generated when Elasticsearch analyzes strings. So by default, when you send a string field to Elasticsearch, it will take it and it will break it down in what is called a tokenizer. So from the whole string, it will break it into words, so to speak, and then it will take that stream of tokens and it would run them through a token filter. And this is what basically the standard analyzer, the one that's used by default, does. So if you send a string like this, then first it will break down, it will get rid of all these characters like parentheses and so on. So you get the words, and then it applies the lowercase token filter, which does the lowercasing. So whenever you search, because at query time, most queries are also analyzed. So when you search, whatever you're searching, for example, with uppercase or lowercase, the actual terms being matched are all lowercase. So you will get the expected results. Now, when it comes to aggregations, which Rafał just showed, these are like the terms aggregation, for example. These will count the actual terms not the complete values of the fields. So it makes sense to run aggregations on fields that aren't analyzed, because you don't, for example, if you have a city name, okay, and you have New York, and you run a terms aggregation and that field is analyzed, you will get separate counters for New and York, and that doesn't make sense. So what you want in this case is not to analyze that field and have New York as a single counter. But the thing is, when you run aggregations, that this sort of inverted index structure isn't appropriate, because let's assume we have this very small thing, and we run a query, and that matches two documents, 2 and 3. Okay, so now if I want to get the counters of how many times each term came up in those matching documents, then I would just have to run through all the term dictionary, and that is not efficient. So what we need instead is a columnar data structure, like you have in other data stores. And on analyzed fields, the only option is to use what it's called field data. So basically, Elasticsearch takes the inverted index for that particular field where you're running the aggregation and uninverts it into this columnar structure. And then it's easy to just say, to just pick the matching documents and count how many times each term appears and return you the results. The problem with field data, there are actually two problems with it. One is that doing this uninversion is expensive. You typically do this the first time you do an aggregation on a certain field. So that means it has to take all the documents that have that field, and it could be billions, and build this structure. And that structure would be in memory. So obviously you could run out of memory, or just the query will fail because Elasticsearch will kind of detect. There's something called the circuit breaker, which will try to estimate how much memory a request will use, and if that's too much, it will just fail the request. So normally when you do aggregation, you would do that on not analyzed fields, and on not analyzed fields, you have an alternative, which is called doc values. And with Elasticsearch 2.0, which is right around the corner, this is the default for not analyzed fields. So basically, we'll build a structure like field data, a columnar structure, but it will build it when you index the documents in the first place, and that will be stored on disk next to your inverted index. So that means you don't bother your heap with that. You don't have to do any uninverted thing for your first query. And then the operating system can be smart and just pull out bits of your index as it needs them and keep them in the operating system caches. So this is much more efficient than field data for pretty much all use cases, certainly for logs. Right. So let me show you then how you would configure this, how you would analyze or not analyze, enable doc values and whatnot. I'll just delete this index first, so we start from scratch. Once again, deleting stuff is fun. And I will just put a new index, and when you put a new index, you can choose how your mapping or schema will look like and what settings you want to put for your new index. So this is quite a lot to go through, but it's not that much actually. So when it comes to mappings, mappings are just another word for schema. Okay, each type that Rafal showed, like we have Apache logs, for example, could have an attached schema. The one thing I want to mention here is that if you have multiple schemas and there are some common fields, for example, like a timestamp, they would need to have the exact same definition, because ultimately all the documents, no matter the type, will end up in the same set of indices. So there you have to have some consistency there. But anyway, within each type, you can define what your properties are going to be. So for example, I'm going to have a timestamp field, which will be a date. I'm going to enable doc values on it. And for timestamps, because the Elasticsearch will basically parse strings and index them as numbers, we can specify what kind of strings do we want to accept. And then we have a bunch of string fields, and this is how you would make them not analyzed, and again, enable doc values on them. If you don't want to define all your types up front, you can also use this _default type, which will be inherited by all the types that you're going to use. Because as Rafal showed you, if you have nothing in Elasticsearch and you just put a document which goes to an index and to a type, Elasticsearch will create that index, and that type will try to auto-detect the mapping and so on. But you can sort of be one step ahead and say, okay, the default mapping will look like this. And again, we will have properties like timestamp. This is the all field that, again, Rafal mentioned, which will sort of be like a catch-all field. If you don't know where to search on, you can search on this. You can disable it, of course, to save some space. In this case, I'm also disabling norms, which are only really relevant for full-text search when you sort by relevancy. But with logs, you typically sort by timestamp. So if you disable them, then you save some space and some memory. And another thing I wanted to show with the mapping is that you can have dynamic templates. And this will let you avoid having to define every single field in your documents, because you can have lots and lots of them. And so, for example, I have a rule field that will match all the strings, all the new strings that are not encountered so far, matching a certain pattern, in this case, everything. And then I would define the mapping that I want to have for these fields. In this case, there will be type string, obviously. I will disable the norms again, and I will also disable field data, because I don't want someone to accidentally run an aggregation on an analyze field and blow up my heap, crash my cluster. Instead, I can specify what is called a multi-field. So it's like a subfield. So let's say I have a message field that is typically analyzed, and I don't have field data on it. But if I do want to do aggregations, then I can have a subfield, message.raw, which will again be a string, but it will not be analyzed, and it will have doc values. So then I can run the aggregations. And I have another rule, which if the thing isn't a string, because it would match the previous rule, then it will be anything else, a number, a date, and so on. And I would enable doc values on that as well. And one more thing, which is related to performance, is setting the refresh interval. Now, Elasticsearch isn't real time. It's so-called near real time. So whenever you index stuff, Elasticsearch has to refresh its view on the index in order to actually give you the results that were just indexed. So by default, it does that every second, and that is why it seems to be real time. The problem is every such refresh can be quite expensive, so you should really only refresh as rarely as you can afford, because obviously if you refresh very rarely, then you will have like a lag and you won't find stuff. So 5 seconds is a decent value for most use cases, but yeah, basically as rarely as you can without kind of affecting user experience. Okay. And another thing, and then we would move on to scaling, is Elasticsearch needs quite a lot of memory. And copy pasting is more fun. So you would go to the, not to the configuration file, but to the etc default file in case you install it from the packages. And here you can configure a bunch of stuff. Most importantly, how much heap do you want to allow Elasticsearch to use? And the rule of thumb is give it half of your total memory and leave the other half for the operating system to use as caches for your whatever you store, doc values and store fields and so on. But in practice, you will want to actually monitor how much memory Elasticsearch uses. You can use something like our SPM to do that, which will show you how much memory Elasticsearch actually uses. You can see that per pool. And in this case, for example, it only uses about half of the memory that we give it. So we could do with less memory and leave more room for operating system caches. And I'll leave this for Rafal to talk about scaling.
Thanks. As we know, a single machine can only handle a bunch of logs up to a certain point. So we actually need the ability, and Elasticsearch provides us with that, to scale by adding new nodes. What we will show you today is what happens when we add new nodes. We'll, of course, use a single machine, but we'll run multiple Elasticsearch nodes. The thing to remember is that each index is actually a more or less virtual thing in Elasticsearch, because physically it is built up of Lucene, small Lucene indices. And those indices are called shards. There are two types of shards, primaries and replicas. The primary shard is what you actually start when you create an index. When you create an index, you specify the number of shards you want the index to be created. So if we specify 5, 10, or anything like that, we end up with that amount of shards, and we can't change them during the lifetime of the index. There are techniques to allow us to change them daily, for example, which Radu will cover, but this is one of the things to remember. The second thing is that we can add replicas, physical copies of the shards that are the primaries. And the good thing is that we can do that while the cluster is live, using the API without any problems. And Elasticsearch will take care of all that stuff that needs to be done, like copying the data, placing the shards, rebalancing them through all the nodes and stuff like that. Because the nice thing about Elasticsearch is that actually when you add new node, it will look at all the architecture of the cluster and try to rebalance the shards in an even way, so the nodes are evenly loaded. This goes both for replicas and primaries. The same thing, if a primary goes down, Elasticsearch will elect one of the replicas for the primary role, and the primary will take the role of and the replica will take the role of the primary until that primary is up, or if another node goes, or there is a place to create that. So let's see how that works. So first of all, it's here. Okay. So first of all, to show you how that all works, I'll use a simple cat API. It's an API that is human-friendly in a sense that it gathers information from multiple sources, multiple internal APIs, and show them with a single request. In that case, I'm using the cat shards, which will show us information about shards of indices available in the cluster. So if we run that, we can see two indices being present. Let's not focus on the Kibana one because it's internal for Kibana. Let's focus on the logs one, which is the one here. So the API shows us a few important things. Of course, the index name, the shards, which those shards are enumerated from 0. So we have 5 shards by default for the index. They are enumerated like 0, 1, 2, 3, 4. And each shard is either a primary, P stands for primary, and R for replica. The state is what the shard is actually, is it working or not? Is it maybe in recovery? The started means that is okay. We have it working and ready to accept data or serve data. And an assigned means that shard is not actually working right now. Why is that? Because by default, Elasticsearch won't put a shard, actually a primary and its replica on the same node. That would be pretty stupid to do if you imagine that you have a node which has a replica and the primary is on a single node and it goes down, you lose data. So this is by default one thing.
I think we have a question there.
Yes?
You keep saying replica and sharding. Isn't that two different things? Isn't replica a copy where sharding is a part of?
Yes, shards, the primaries actually, the primaries, let's call them. The primary is that initial, what you when create index, those initial shards that are. The replicas are copies of those shards. This is what Elasticsearch calls them. This is not something what we just take. This is how the glossary of Elasticsearch.
Well, basically, an index is divided into multiple shards. So that the ones that are leaders, so to speak, are called primary shards. And then you can have a number of replicas. Yes. So for each primary shard, you would create 1 or more copies, or 0 or more copies.
Yeah.
Does that kind of clear it up, or okay?
And in addition to that, we have the information about the number of documents in the shards, the store, which means how much they weight, the IP address, and the node. And now let's see what happens if I start another node. This is done very easily. I can just go to Elasticsearch directory, the installation directory, and run this command. Is it? Ah, okay, I have it. So I run this command bin Elasticsearch, and I provide a node name. And let's wait for a bit. What Elasticsearch does now, it's tried to find a master node. They saw each other, connected to each other, did the replication, and we're back here. And now let's look at the shards. Yeah. This is because of that log stash index. Anyway, so what you can see here, it's maybe not that visible, that all the shards are now started, both the primaries and the replicas. And some of the shards were placed on that velocity 0.2 node, the new one. Those will be the replicas because of how, because we had primaries already assigned to the first node, and then the second node joined the cluster, and Elasticsearch was able to actually assign all the replicas that were not assigned, copied the data to those replicas, and start them using, and now we have one primaries and their copies. Now, if we would just start another node, this is Kafka, right?
Yeah, we don't want Kafka yet.
Yeah, not yet. Where is Elastic?
Yeah, there it is.
Okay. So if we would now do the same but with another node 0.3, we would just, again, wait for it to start, to join the cluster. Okay, with a different UID. Okay. So if we would run now shards, we could see a bit that now the shards were spread through multiple nodes. We can see that some of the shards ended on the 0.3, the new nodes. Some of the shards were left on the 0.1, some on the 0.2, and stuff like that. So basically, Elasticsearch took the new node, joined it into the cluster, and rebalanced all the shards using the internal algorithms to have it more or less even. Now let's try and see what happens when we actually delete the nodes. One thing to do before we start deleting them is altering the settings of Elasticsearch, because we don't want to wait. By default, Elasticsearch has a mechanism that prevents a dance of the shards. You can imagine a situation where you, for example, restart the node, and Elasticsearch sees that, and all of a sudden, it starts to move the shards around because one of the nodes was down, so the environment is not even at all. It starts to move the shards around, and then the node again joins in the cluster, and again the shards are moved. Because of that, there is a timeout, and so-called delayed timeout, which is by default set to 1 minute, which tells Elasticsearch how long to wait before doing those processes. Because we don't want to wait today, we'll just set it to 0 by using that setting. This is, again, a nice thing about Elasticsearch, that most of the useful properties can be changed dynamically when the cluster is actually running. So we'll just run the settings command, Elasticsearch set acknowledged, and we can just start removing nodes. Wait, just a second. I'll take, again, the shards command, and again, we'll show that. This is the stuff before killing the nodes. And let's start by killing not the third node to just see, but the second one. So now what Elasticsearch did is it actually migrated, it didn't migrate, it created some of the shards that were on the node 0.2 that were primaries as well. So Elasticsearch just promoted some of the replicas that were on 0.3 and 0.1 to being new primaries, and the whole environment is still working. A bit less performant because we have less nodes, less hardware, but still that works. If we now kill the third node, the situation will get back to that point where we started, and we have unassigned replicas, but still the primaries are there, so we didn't lose any kind of data. We are still operational, so even if we do rolling restarts or something fails, which happens, we're still good.